is an experiment, as a initial experiment. Hopefully there will be more of this ilk that we did in order to test a rather counterintuitive prediction of IIT, which is that changes in connectivity without ideally changes in activity should change the way experience feels, in this case, spatial experience. So if you strengthen the connections in this little grid, once you unfold it, you get a cause effect structure that will correspond to a more contracted experience of space. And so we used some tricks. We basically used very rapid flashing of two bright dots at a particular location in the visual field during training. And before and after training, we checked how psychophysically, how far apart two dots presented, for instance, here were from each other compared to other two dots. And so we could do that pre and post-training testing. The training is supposed to produce a strengthening of connections indicated here between the corresponding topographically mapped regions in visual cortex, presumably mostly primary visual cortex. And indeed, we observed that for subjects, the two spots presented after training, where the connection was stronger, looked closer. The most important test is down here. If you stimulate now in two far away regions of the visual field, where you produce no potentiation, no flash, rapid flash, and so on and so forth. So presumably you didn't change the activity patterns that you elicit here when you present these two spots before and after training. All you changed was the strength of the connectivity here in the middle. Even so, as predicted by the theory, space would contract. So this is the kind of experiments, for instance, which are counterintuitive. You change connection strength, you don't change activity patterns to the extent you can actually have that, and the experience will feel different. So I will finish with the predictive power right here, at least some examples of the predictive power, not just explanatory power, but predictive power. Most of the work that we did from the start was to look at big stuff. When you're conscious versus when you're not, when consciousness is present or not. Will some poor man's proxy of phi, of integrated information, indeed behave as predicted? High when you're conscious, low when you're not. So we developed an approach with TMS-EEG in which we would measure the complexity of the response across the brain with 60 channels of EEG. This was done with Marcello Massimini, who has been continuing this line of work. You can see here a complex response in the EEG, and here is sort of a compressed version over time. You see many brain regions, cortical regions being involved at different times, typically up to 400 or 500 milliseconds. The same subject, when unconscious early in the night, the response is much simpler, as you can see here. And in practice, what happens is there is a strong response, but it's only local. It stays there where you stimulate, and it doesn't really propagate anywhere else. It dies off very quickly. Okay, so that was according to the prediction of the theory. And then from then on, more difficult experiment, we tried to see whether when you started dreaming, for instance, in REM sleep, the response should go back to be similar, indicating high integrated information to when you're awake. And indeed, it did, unlike an unconscious state of sleep. And then anesthesia. Here you see midazolam anesthesia. That was the first set of experiment we did in Madison, and propofol, xenon, and notice ketamine. So these three anesthetics, where the subject is not there, is really gone, led to a response which is not complex as predicted by the theory. The critical one was ketamine, because it's an anesthetic which is not really used in adults now, but it was initially. It produces complete unresponsiveness. You can do surgery, but subjects dream very intensely, which is why it's not used, because it can be also a bad trip, so to speak. But you're conscious, and the response, even if the person is unresponsive, the response of the brain suggests high complexity, high phi. This is just to tell you that this can now be done in rodent. These are our data using neuropixel recordings in a rat. And here you see the response, the evoked response, the local field potential. And here the units, every little dot is a unit firing across the depth of cortex, hippocampus, and thalamus. And you can see that in the cortex, when the animal is in deep non-REM sleep, there is an off period. So we can confirm that units stop firing for roughly 200 milliseconds after the initial response, when the animal, in this case, in non-REM sleep. For that matter, that's also true for sevoflurane, dexmedetomidine anesthesia, and it's back in REM sleep. So an index, the perturbational complexity index that quantifies this complexity, is indeed behaving just like in humans, high in wake and REM, and low in the other condition. And the reason it's low is because you break causal interactions during the off period in non-REM sleep. By the way, this we also simulated quite some time ago. Now we have more recent simulations. Basically we understand reasonably well what's going on in the 3 layers of cortex, 3 main layers, supra, infra, and layer 4, and then in the thalamus. In sleep, you get this off period, this brief, everybody shuts off, that kill the causal interactions and therefore consciousness. This is just a summary that across hundreds of subjects now, you can see that if you measure this index of integrated information, a very crude index, it's always high. These are different subjects when subjects are awake, even neurological subjects with locked-in syndromes of cortical strokes, emergence from the minimally conscious state, and importantly, when they are conscious but unresponsive, like ketamine and dreaming. But it's always low when they are in an unconscious situation, non-REM sleep, midazolam, xenon, and propofol anesthesia, with very high sensitivity and specificity. There's really nothing sort of like that. So that was a prediction of IIT, and then it can be used, for instance, in vegetative patients to find out where behavioral responsiveness is not really a great guide, whether they may be there or not. If the values are 0, then presumably there is nobody there. The values are low, but like sleep or anesthesia, maybe there is a chance to wake up these people with deep brain stimulation or drugs. And when the values are similar to what we observe in ourselves when we are conscious, there are reasons to believe that these people are there, as we know from other paradigms, and to try to use brain-machine interface to communicate with them. I want to finish the IIT part by showing you something that we've been doing for quite a while now. It's not published yet, but it's actually very important when it comes to then possible tests of free will. So here we were trying to get a sort of slightly better measure of phi, more explicitly phi integrated information according to the postulates of IIT, using what is available, which is say 7 Tesla and 3 Tesla data from the Human Connectome projects. On a lot of subjects, these are high quality data. Of course, they don't have the ideal temporal and spatial resolution, but they are already something rather than nothing. And we did, for instance, resting state or tasks. And what you can do, if you do at the voxel level, you can see that you have 32K voxels, 32,000 per hemisphere, and you can approximate with lots of assumptions and approximations the value of phi. You can literally measure some kind of crude but reasonable proxy of phi. And if you apply it, for instance, to posterior cortex as a whole, the values are very high. This is a logarithmic scale. If you apply the same measure to prefrontal cortex and the insula here, it's a particular group of voxels that we might be interested in, the values are much, much lower. If you apply to the cerebellum, they're incredibly low. And importantly, if you apply the measurement to the cortex as a whole, far from going up, they go down. And that is because, evidently, while everything is connected and integrated, if you wish, it is not as irreducible, the cortex as a whole, as some parts of it. This is literally, again, what phi measures when it tells you what the borders are of what exists maximally, okay? And then if you actually go and subject by subject, you find out with an algorithm which is far from perfect and far from comprehensive, essentially based on simulated annealing, what is the set of voxels that is maximally integrated within each subject, and you plot it across 160 subjects, and you say, what are the voxels in the brain that are most likely to be part of this maximally irreducible set, which according to IIT would be the physical subset of consciousness, or as we call it, the main complex. You see in red and yellow and green here, that is primarily located in posterior cortex. In fact, this is in the resting state, when subjects are just, going through their mind without watching or hearing anything in particular. Here's watching a movie. It's very much the same regions, but extends more, for instance, toward auditory cortex and higher order visual areas. And in fact, this is true also at 3 Tesla. And here we have data about several different tasks. Again, this main complex, at least probabilistically, is primarily in the back. And notice it has nothing to do with which areas get activated when you are performing the task. When you're performing the task, all kinds of areas, including in the front, can get strongly activated. These are the areas that are maximally integrated of highest phi, according to IIT. So this is a little bit of the footprint of what is the substrate of consciousness in the brain, purely based on first principles, based on whatever is maximally integrated has the highest phi. Now, is that correct? Of course, it is correct if and only if the empirical data about the substance of consciousness are in agreement. Now, there is no agreement on anything with consciousness, as I suspect you know, but we certainly try to, and there are data in the literature that can be interpreted in the proper way, I think. What we try to do is to develop a within-state paradigm, because it avoids lots of pitfalls and confounding factors that are involved when you are using report paradigms, task paradigms, or compare wake to sleep directly or wake to anesthesia, where so many more things change than just consciousness, okay? So our approach was to take the only situation in which we are in roughly the same state, for instance, non-REM sleep, immobile, sort of unresponsive, the brain is showing slow waves and spindles, everything looks sort of the same, and you're performing no task. But sometimes, 2/3 of the time to be precise, you are conscious. If I wake you up, you report that you were dreaming. And 1/3 of the time, you are not. So we can do a proper within state contrast. And we focus on the last 20 minutes so we can get a good EEG correlate of that. And the EEG correlate in non-REM sleep is that when you are unconscious, when you're not dreaming 1/3 of the time, there is slow wave activity in the back. We can't be exactly sure about which areas, okay, because it's an average over many subjects, over many dreams, so to speak, but it's primarily in the back. And the slow waves, of course, as I showed you before, are these off periods in which neurons cease firing and they break down the causal interactions in posterior cortex. So that fits with the theoretical predictions. This is REM sleep, which looks radically different on the EEG, but sometimes you don't dream in REM sleep. And when you don't, again, you tend to have slow waves in the back. Now, these are lesion data. And the most classic is the Brickner patient here from the 1930s that was studied for a long time. There was a whole book about him. And then there was, the pathology. And in essence, this is a person who had meningiomas that were producing increased intracranial pressure. And the surgeons at the time took out first the entire left prefrontal cortex, except for Broca's area, and then the entire right prefrontal cortex. You can see what's left here. And clearly, this subject did not have any big problem with consciousness. He was very much conscious as before. The only thing he had was a personality change and some inflexibility and perseverance, which is what we now call it's a frontal syndrome. At the time, it was actually even argued whether he had a syndrome at all. Hebb and Penfield, not exactly two lightweights, thought that there was nothing wrong with the person, nothing was wrong. And Brickner, the neurologist, has to push to say, no, there is something wrong. And it has to do with personality and some functions, but certainly not with consciousness. By contrast, if you consider both traumatic and lesions and anoxic lesions, when they involve the back, like for instance, much of the posterior corpus callosum and then the regions associated with it, which degenerate, then the subject remains unconscious basically forever. The odds of coming out are minimal. So lesion evidence also fits, and this is just one meta-analysis that was recently performed of stimulation data from all over the cortex and the medial temporal lobe in human subjects. And you can see here in red that the areas where you produce some changes, so-called eloquent cortex, and in particular changes in the experience, are again primarily in the back. There may be many reasons for it, but in essence, recording studies, lesion studies, and stimulation studies are sort of consistent in saying that the back seems to be particularly important as the substrate of consciousness, which would fit with these tentatively very high values of phi. So I'll finish the first part by just pointing out, which will be important for later, one key implication of IIT with respect to difficult questions about presence of consciousness in other species very different from us, in cortical organoids, or is there such a thing as collective consciousness? The only one I want to point out is computer consciousness. Okay, now with artificial intelligence, especially with artificial general intelligence, we are getting to the stage in which computers are becoming more and more functionally equivalent to us. They can do most of the things we do, sometimes even better. They're not there yet, but the key point that follows from IIT, it's an implication very much like the one about free will I will discuss next, is that if IIT is right, a computer, a super powerful computer that might even completely simulate in detail the activity of the neurons in my brain by having a precise notion of the connectivity and their properties, will not be conscious at all. This